Hey there, science fans! Welcome today to be guided through the exciting world of chemical bonding. Have you ever wondered what holds atoms together to form molecules? That's the magic of chemical bonds. Understanding how atoms bond is crucial for comprehending the properties of matter and the reactions that create the world around us. In this journey, we'll explore the fascinating concepts of bond polarity, formal charge, and Lewis structures. We'll uncover how these concepts help us predict the behavior of molecules and their interactions. So buckle up and get ready for an electrifying adventure. Let's dive in. Imagine two kids playing tug-of-war. One kid is bigger and stronger, so they pull the rope harder. In the world of atoms, electronegativity is like that strength. It's the measure of an atom's ability to attract electrons in a chemical bond. Each element has its own electronegativity value. Elements like fluorine and oxygen are like the strong kid. They have high electronegativity and pull electrons towards themselves. On the other hand, elements like sodium and potassium have low electronegativity, letting go of electrons more easily. Electronegativity is a key player in determining the type of bond that forms between atoms, so let's explore those next. When atoms bond, they share electrons. But this sharing isn't always equal. Remember the tug-of-war? If the atoms have similar electronegativity, they share the electrons fairly equally, forming a nonpolar covalent bond. However, if one atom has a higher electronegativity, it pulls the shared electrons closer, creating a polar covalent bond. This uneven sharing results in a separation of charge, with the more electronegative atom having a partial negative charge, delta, and the less electronegative atom having a partial positive charge, D+. We can even calculate the difference in electronegativity, Dn, to quantify bond polarity. A larger Den indicates a more polar bond. For example, the Den for HKl is 0.96, indicating a polar covalent bond. There's a table for each oxidation number. Now let's talk about oxidation numbers. Think of them as a way to keep track of electrons in a molecule. They tell us how many electrons an atom has gained or lost, either completely or partially, compared to its neutral state. In a molecule, the more electronegative atom is assigned all the shared electrons, giving it a negative oxidation number. Conversely, the less electronegative atom is considered to have lost those electrons, resulting in a positive oxidation number. Understanding oxidation numbers helps us predict how atoms will react and form compounds, which is super important in chemistry. So I'm currently working on a form that requests homework commissions, which means I'll do your homework for money. I'd love to do work for free, but honestly, I'm a dirt poor college student. So if you're interested, look in the description to see if the commissions are out yet. I'm thinking about payments being through Cash App. Please, I'm a broke college student that needs money. Now that's out of the way, let's get back to the video. Formal charge, determining the best Lewis structure. Lewis structures are diagrams that show the bonding between atoms in a molecule. They help us visualize how atoms are connected and how electrons are distributed among them. This is crucial for understanding the molecule's properties and reactivity. But sometimes we can draw multiple Lewis structures for the same molecule. These different structures are called resonance structures. Each resonance structure represents a possible arrangement of electrons in the molecule. How do we know which one is the best or most likely structure? This can be confusing because not all resonance structures contribute equally to the actual structure of the molecule. That's where formal charge comes in. Formal charge helps us determine which resonance structure is the most stable and therefore the best representation of the molecule. Formal charge is a way to assess the distribution of electrons in a Lewis structure. It helps us understand how electrons are shared or transferred between atoms in a molecule. It tells us how many electrons an atom owns in a structure compared to its neutral state. This comparison is essential because it helps us identify any imbalances in electron distribution. We calculate formal charge for each atom using the formula: valence electrons minus the total sum of non-bonding electrons and of bonding electrons. Or you can think about it as sticks and stones make a home, where sticks are bond lines and stones are any lone pairs, and where the home is the valence electrons. So sticks plus stones minus the home or valence electrons. This formula allows us to quantify the electron distribution in a molecule. The Lewis structure with formal charges closest to zero and with any negative formal charges on the more electronegative atoms, is considered the most stable and therefore the best representation of the molecule. This stability is crucial because it indicates the most likely arrangement of electrons, which in turn affects the molecule's behavior and interactions. Understanding and determining the best Lewis structure is a fundamental skill in chemistry. It allows scientists to predict molecular properties, reactivity, and interactions with other molecules. By mastering this skill, we can gain deeper insights into the molecular world and make informed decisions in various chemical applications. So, next time you encounter multiple Lewis structures for a molecule, remember to use formal charge to find the most stable one. This will help you better understand the molecule's true nature and behavior. Happy structuring! Lewis structures and stability, the octet rule and formal charge. The octet rule states that atoms tend to gain, lose, or share electrons to achieve a stable configuration of 8 valence electrons, just like noble gases. This rule helps us predict how atoms will bond and form molecules. When drawing Lewis structures, we aim to satisfy the octet rule for each atom while minimizing formal charges. Structures that follow the octet rule and have minimal formal charges are generally more stable. Understanding the relationship between Lewis structures, formal charge, and the octet rule allows us to predict the stability and reactivity of molecules. Sigma and pi bonds, the building blocks of covalent bonds. Covalent bonds are essential in the world of chemistry, forming the backbone of countless molecules. Covalent bonds, where atoms share electrons, are formed by the overlap of atomic orbitals. This sharing allows atoms to achieve a more stable electron configuration, similar to that of noble gases. There are 2 main types of orbital overlap, sigma and pi bonds. Understanding these bonds is crucial for grasping how molecules are structured and how they interact with each other. Sigma bonds are formed by the direct head-on overlap of atomic orbitals. This type of overlap allows for the maximum overlap of orbitals, resulting in a strong bond. They are the strongest type of covalent bond and form the axis between the 2 bonding atoms. This axis is a straight line that connects the nuclei of the bonded atoms, providing a stable and robust connection. Pi bonds, on the other hand, are formed by the sideways overlap of atomic orbitals. This type of overlap occurs above and below the axis of the bonded atoms. They are weaker than sigma bonds and exist above and below the axis between the bonding atoms. Despite being weaker, pi bonds play a crucial role in the chemistry of multiple bonds. A single covalent bond always consists of 1 sigma bond. This single bond is the simplest form of covalent bonding and is found in many common molecules. Double and triple bonds involve 1 sigma bond and 1 or 2 pi bonds, respectively. These multiple bonds are found in more complex molecules and are essential for the structure and function of many organic compounds. Double bonds with 1 sigma and 1 pi bond add rigidity to the molecule, while triple bonds with 1 sigma and 2 pi bonds create even stronger and shorter connections between atoms. Bond length and bond energy, understanding bond strength. Bond length is the distance between the nuclei of 2 bonded atoms. It's like measuring the distance between 2 friends holding hands. A shorter bond length indicates a stronger bond. Bond energy, on the other hand, is the energy required to break a bond. Imagine trying to separate those 2 friends. A higher bond energy means they are holding on tighter and the bond is stronger. Bond length and bond energy are inversely related. Shorter bonds tend to have higher bond energies. Additionally, bond order, whether single, double, or triple, also affects bond strength. Triple bonds are the shortest and strongest, while single bonds are the longest and weakest. Conclusion. Putting it all together. Congratulations, science explorers! You've made it through an incredible journey of discovery and learning. You've journeyed through the fascinating world of bond polarity, formal charge, Lewis structures, and more. Each concept has added a new layer to your understanding of chemistry. Remember, electronegativity dictates how strongly atoms attract electrons in a bond. This fundamental property helps us predict how atoms will interact in a molecule. Bond polarity arises from differences in electronegativity, leading to partial charges. These partial charges are crucial in determining the behavior and reactivity of molecules. Oxidation numbers help us keep track of electron transfer in molecules. They are essential for understanding redox reactions and the overall balance of chemical equations. Formal charge helps us determine the most stable Lewis structure. By calculating formal charges, we can predict the most likely arrangement of atoms in a molecule. Lewis structures illustrate bonding and help us understand molecular stability. They provide a visual representation of how atoms are connected and the distribution of electrons. Sigma and pi bonds are the building blocks of covalent bonds. Sigma bonds form the framework of molecules, while pi bonds add additional stability and reactivity. Bond length and bond energy are indicators of bond strength. Shorter bonds are generally stronger, and understanding this relationship helps us predict molecular behavior. By understanding these concepts, you've gained valuable insights into the fundamental principles governing chemical bonding. This knowledge is the foundation for more advanced studies in chemistry. This knowledge will serve you well as you continue your exploration of the amazing world of chemistry. Whether you're conducting experiments or solving complex problems, these principles are your guide. Keep those scientific minds curious and never stop asking questions. The world of chemistry is vast and full of wonders waiting to be discovered. Your journey has just begun, and there's so much more to learn and explore. Have a nice night, and be sure to have a good night.